Hey everyone, I've decided to release this video early for any students already in section 4.4. This video will be a piece of the part 1 video for section 4.4. I hope the contents help you understand the concept of concavity. So hey, here I've made an animation. As you can see, we have the graph of the function y equals x cubed minus 4x. The red line is the line tangent to the function at the point P. In a second, I'm going to start an animation I made with GeoGebra. It will move the point P towards the critical point. Before I do it though, I'm going to ask everybody to take a second and ask themselves, what's going to happen to the slope of the red line as P gets closer and closer to that critical point? Also, what does that mean about the second derivative at the point P? Please pause the video and give yourself a minute to think about the answers to these questions. Alright, you've thought about it. So there's a big button that says push me. Generally, I don't advise listening to inanimate objects, but let's go ahead and click it anyway. As we watch it again, notice that the derivative at the point is decreasing to 0. This makes sense since it's going to a critical point where the derivative has to be 0, since f is a polynomial, and hence its derivative exists everywhere. Since the derivative is decreasing, that means the second derivative, which is the rate of change of the derivative, must be negative, based on what we discussed in 4.3. Okay, so we're going to see another animation. This time I'm going to move the point P from the critical point down to the origin. Again, I want you to take a second and ask yourself, what's going to happen to the slope of the tangent line as you head towards the origin? Also, what does that mean about the second derivative? Okay, here we go. Let's push the button. Okay, well, it got steeper, but in this case, it got steeper in the negative direction, so it is still decreasing. That means that f double prime is negative on this interval. For the next two clips, I'm going to go a little faster. Okay, the first clip is going to take us from the origin to the local minimum. The second clip is going to take us from the local minimum up towards infinity. So take a second and ask yourself, what's happening to the slope of the tangent line on each of the next two intervals? Also, what does that mean about the second derivative? Unlike before, now the slope is increasing, which means the second derivative must be positive. This makes sense because the slope starts at -4 and ends at 0. This time, we see that the slope of the tangent line is increasing, which is the same as saying the second derivative is positive. So let's look at the fourth clip really quickly. Perhaps you can guess that the tangent line should increase in slope, which implies the second derivative will be positive. So let's summarize everything we've learned and try to draw some conclusions from it. First of all, on the first two intervals, the second derivative was negative. On the next two intervals, the second derivative was positive. Also notice that on the first two intervals, our function is concave down, and on the second two intervals, our function is concave up. So here's the animation one last time, but this time it also displays the second derivative's value at each point. Finally, I want to draw your attention to what is happening at x equals 0. Before x equals 0, the second derivative is negative. After x equals 0, the second derivative is positive. This means at x equals 0, the second derivative must also be 0. We call points like this inflection points.